So that's exactly, we start by compute the whole data set's information entropy. That's our standard formula, right? So represents class. We have M classes in this data set. Then conditional entropy is if we introducing, for example, age. If we use age to split data into these V partitions, what's our entropy now? This conditional entropy is calculated as a weighted sum of every partition's information entropy. Okay. So then before the split using attribute and after the split using the attribute, we can compute the difference between the certainty or uncertainty. We get a gain, which is called information gain. If we split on this attribute A, how much uncertainty that we have reduced? Okay, questions? So in a more visual way, we have the initial data set. We have the entire data set's information entropy. Now we use age, for example, to split into smaller 3 partitions. At the beginning, we have 4 classes. After the split, some partitions only have 2 classes. Some partitions becomes pure, only have 1 class. And then we can compute the conditional information entropy after this split, again, weighted sum. And we find again the before and after, how much certainty that we have obtained. Questions?
I have a question.
Sure.
That values are like, it is like the number of data in DJ divided by D, or number of classes in the
number of observations.
Okay.
Yeah.
Okay.
Yeah. V is partition.
Okay.
So for every partition, we compute the entropy here, and here we weighted sum.
Okay.
We weight based on their numbers, counts. Okay, good. Now we can move on. So this is a concrete example that we're talking about who's going to buy or not buying computers. So this is our class label. We have age, income, student, credit rating as features. So given this data set, not knowing anything, our data set has an information entropy. The split between buying computer and not buying computer is 9-5. And we can compute the information entropy for this entire data set. That gave us 0.940. Next, we're going to select which of the attribute going to be the attribute that we're going to use to split the data. We start with age. So using age, we can see the factors in age have 3, or have less than 3. So there are 3 levels, different ages. And using age as a condition, we know the positive buying computer and not buying computer has a different distribution than the original data set. So age less than 30 years old have 2 buying computer, 3 not buying computer, right? So for every small portion, small group that we can compute its information entropy using exactly the same formula here, except this time we're using 2 and 3s to replace the numbers here. So it will be 2/5, 2/5, 3/5, 3/5. That will give us the information entropy for this portion. Do that for every one of those. And then we can compute after the split, the conditional entropy. It's a weighted sum, as we can see. So total we have 14. This portion has 5. This portion has 4. This portion has 5. So this is our conditional entropy. So take the difference, we get our information gain to be this much. We'll do the same thing for income, for student, for credit rating, and we find information gain for each one of those attributes. And then we compare to see which one gave us the greatest gain. And age, look at the numbers, we can see that age gave us the largest gain. Therefore, age is our next split attribute. We will split according to age, like what we did here. And then for every data set partitions, we select the next level of attribute to see how are we going to split this portion into smaller subset to make our, to increase our certainty, decrease the impurity. Does that make sense? No questions? Okay. Earlier we talked about those examples looks like all discrete attributes. A lot of times you also could encounter continuous attributes. We have made the age to be into different things, but we could actually start with ages to be real values, concrete values. So when we have continuous valued attributes, there is also an easy way to split. Using this attribute, we can first sort the values of A in increasing order. Then we test the midpoint between each pair of adjacent values. It's considered a possible split point. And we test every one of them and decide which one give us the greatest gain. Then we can split on that point. So this will give us 2 branches. So any value that's greater than our splitting value or any value that's larger than our grading value. Question? Okay. So this example shows this is the police shooting data that we did before, and this was the trees that we built. And we can see this age has a continuous variable, and it was splitted reasonably. We talked about information gain. Information gain measure has a bias, which is because it's based on the information entropy, it's biased towards attributes with a large number of values. One extreme example would be using student ID to split. Every student going to have a unique ID. So this attribute alone will split the tree to the single node, to the single leaf node, because every, student ID are basically unique. To address this question, this bias, the system would always select attributes with high cardinality to split. To address this issue, we add another correction factor here called split info. Split info measures how many groups this this attribute going to result in. The greater the number of groups result in, the smaller the gain ratio going to be. As we can see, this is a denominator. So here again, V is number of groups or the portions that will be or branches that result from this attributes. Those are the counts within each portion. So with adjustment, so this example show that we can actually compute if we use income as, there's 3 levels of income. So if we use income as, test income as a splitting character or attribute, we can compute the split info and divide it by the original ratio that we have, another attribute, gain ratio, that we can use to assess, to select attribute. Question? Okay, so this is, yes?
Where is this 0.02 coming from?
On this? Are you talking about this value?
Yes.
Yes, here. So remember, yeah, we calculate gain for age. We also calculate information gain for income and all that. When we use gain ratio, we will divide this number by its split info value, split every one of those, and then compare again to see which one is actually the best. But in this case, our age, income, and the student, none of those has a very large cardinality. So I would not expect, again, split info would change the decision here. But if you have certain attributes that has much larger cardinality than others, that could make a difference in terms of which one of the attributes turned out to be the best attribute to split.
So is the, like, if when we have student ID, we should exclude that from consideration? Is that the
for example, student ID should just simply be excluded. You don't want the computer to spend the computational effort on an attribute like this. It's unique to every observation, right? So those should just simply be removed. Others, because decision tree do have this set effect or drawback when you have a high cardinality attribute. Finding different combinations of those attribute value to split the tree can take a long time. In our example, when I did police shooting data using state, we only have 51 states, right? It will make the computer run like hours. Once I removed this state attribute, it runs in like less than a second. So using decision tree, we would first discretize. And some decision trees has discretized functions built in to discretize the values to reduce cardinality. Are we good to move on? Okay.
Is
okay.
The intuition there that if you look at something like student ID, and you split based on student ID, your classes will be pure because each observation will have, say, one value of race, but that's not really a good way to make a decision. Is that sort of the intuition that is not giving you really insight as to why is pure?
Right. The intuition here is new examples will never have the same student ID, like your training example has, right?
Thank you.
So if you have a value with very high cardinality, every value is very unique, the value itself may not offer you that much information. Rather, a small range containing that value could be more robust for a classification task. Does that make sense? Like if you think about people's height or grades, you know, what's the difference if you're 1.61 meters tall versus 1.60 meters tall? There's really very little difference. If you put it to, it's just discretize your value into 1.6 meter range, then you cover lots of noises, variations, and your model going to be more robust. That next time you can classify a person who's 1.62 meters tall. Okay, so so there are lots of decision tree attribute splitting metrics has been developed. We have talked about information gain and gain ratio. And the third one we're going to introduce is Genie, Impurity Index. This is also the last one we're going to introduce. Those three are used very widely and very frequently and implemented widely in the existing tools. So we thought we should introduce those. Genie impurity is a different way to measure the uncertainty. In this case, they call it impurity, how impure a class or a group, a data set is. Genie impurity index formula is here. Here, n represents the number of different classes. So the Genie index is 1 minus the sum over all classes, the probability distribution of that class. So among all the examples, how many examples falling into that class? Genie index is a value from 0 to 1. Genie index will be 0 when the data set is really pure. There's only one class. Again, the idea of using Genie impurity index is very similar to the information game. We first compute Genie index on the entire data set. Then we choose which attribute that we want to split on. And with that split, we compute another sort of conditional Genie index conditioned on this attribute, A. The difference here is Genie index, using Genie index, you always only split attribute into 2 subsets. We're not going to do multi-way split, only 2. So here you will have, so instead of the sum over all partitions, you have basically branch 1 and branch 2, or subset 1 and subset 2. Okay. The reduction impurity will be computed by taking the difference between the original Genie index and the split after split Genie index. The greater the gain, the greater the difference, the greater that we can reduce the impurity, the better this attribute is for our split. I don't know if you have question on how to split A into 2 subsets. If we go back to what we talked about way before the break, yeah, here. So we can see this is a multi-way split that you can split based on every unique value this variable has. Or you can see whether this is greater than or equal than color within a set that can force things being split into 2 binary conditions, which is what is used in Genie index. Another way of saying that is when you use Genie index, you always end up with a binary tree. Every node will have 2 branches sticking out from that node.
Yes. I have a question. Do we need to worry about the information, the coordinality of the data when we use Genie impurity?
Yes, it has roughly the same because here the Genie it's less so, but still has, because it falls things into 2 subsets. So you will not have the exactly same situation as the information game problem. Yeah, it addressed some of the issues.
Okay.
So
in the previous slide, the PJ2, is that like the probability
squared? Yeah. So that question is answered here. I don't know if we want to go into this detail, but to understand the intuition behind Genie impurity index, Genie impurity index estimate the chance an element would be incorrectly labeled when it is labeled according to the label distribution. So this is a probability or the proportion of if we have a 3-class problem, proportion of the first class in the data set. That would be our probability of choosing class 1 being our label. When we do that, we actually we have this much of a probability of label that data wrongly. So this is the probability that when we choose A, we should have labeled either 2 or 3. Obviously, we could also choose that example to be class 2. Oops. But the true class label being 1 or 3. Sorry, this should be 3. The third type of error that we could make is a class, we decided it's class 3, but it turns out to be 1 or 2. If we generalize this into an N-class situation or P-class situation here, you can see how this formula is derived. So basically, Genie impurity index estimate the chance. If we're using the class distribution to label the data, what's the chance for us to be wrong? It still measures how messy the class, a data set has a mix of class labels. And it has, in practice, it's showing in theoretical, if you do mathematical derivation, you can see that Genie is highly related to the information gain measure. And in practice, we see Genie index and the other two indexes give very similar decision trees. A small advantage of Genie index is it doesn't need to calculate log, so it's faster than information gain measures. Okay, so we have example here to see how to use Genie index to make two-way splits. Still using our buying computer example, yes and no. So starting the Genie index for the entire data set is this much. The class distribution for yes class and no class. And then if we use income, we can try, because income has 3 different values or factors, low, medium, and high. So we can say, let's split between make a low and medium one branch and high the other branch. So this gives us this result. So we're using, I think we have 4 highs. So here, this 10 covers all the low and medium. This has high. So low and medium goes here and high goes here. This is the 2 branches. And we compute the Genie impurity index. And obviously, this should be the same as that, right? This is just the complementary set to that set. And we do that for all other possible combinations, the low-high combination and medium-high combination. Compare those 3, we find which value is the greatest. This one. Okay, yes. So our we're going to find, earlier we said we're going to find the value that gave us the attribute that gave us the greatest reduction in impurity, because this Genie D will not change, right, for a data set. Therefore, we want the smallest Genie index for a split. So here, when we look at all those Genie split index, we found the lowest value, which is this one. So we will split the 2 branch will be the income will be either low or medium, or the income is high. That's how we are going to split the A node into branches. Questions? Okay. Yeah, I talked about this already. All those generating optimal tree is NP complete, meaning it's very, very hard. Nobody has found a method to do that. An optimal tree means a tree that will give you minimum number of tests to classify an input correctly. Since the optimal tree cannot be that found in polynomial time, all the decision trees made so far using this greedy search method to grow the tree. There's no track back. We will make a decision, move on, make a decision, move on to grow the tree. Shallower trees, some decision trees are designed to grow shallower trees. They're quicker to learn, but deeper trees tend to be more accurate. However, it risks overfitting. So there's all kinds of trade-offs. Among the three measures that we studied, they all give very similar performance in general. It could perform differently on one specific data set, but in general, we don't see one to be superior than others. They all have different kind of biases which I think we mentioned earlier. There are also other attribute selection measurements. Big decision tree has such a long history. All those methods has different have different features, but in general they do not. None is significantly superior than others if you apply it in multiple kind of different classification problems. In machine learning, a lot of times we have lots of machine learning algorithms devised, and people often ask which one is the best. It's really hard to answer. There is not one that's best in all circumstances. So a lot of times the first thing we do when we have a new task is we try a lot of different methods and see which one has a better chance to give good performance, and then we work on that. We try to add features, address issues, try to make that model work better. So even though there's many decision tree algorithms, I think the most popular ones are still the very classic ones, the CART, for example.